Okay, 11.1. This formula is a little weird. Sorry, I thought we were done with the crazy ones, but it's honestly, it's not terrible, not compared to some of the stuff we've done. We know the difference between independent and dependent samples. Dependent samples or independent are the next thing. We did dependent last time. So, in 11.2, we dealt with dependent samples. We had matched pairs. So our data was related in some way. So, put my slides here. We have two examples. We're going to decide if these are independent or dependent samples. We're going to get one of each. So we have Joliet Junior College has decided to implement a course redesign of its developmental mathematics program. Students either enrolled in a traditional lecture or a lab-based format. There were 1,200 students enrolled in traditional and 300 in the lab. Once the course ended, the researchers determined whether the students passed the course. And the goal is to see whether the proportion of students who passed is different for each section. So, sorry, I can't read out loud. Do we have an independent or dependent sample? Are we matching these people in any way, or are they just in their own little groups? I say this is an independent sample. We have students assigned in each thing. We're not like matching person to person. Another way we can tell is we have 1,200 in group A, but only 300 in group B. If we were to have a matched sample, we'd have to have the same amount in each one so we can match people. So yeah, this guy's independent. Compare them. All righty. So we already know this is going to be dependent, but let's kind of see why. Products are purchased on are products purchased on Amazon less expensive than those purchased online at Walmart? I can tell you no, as I've shopped both this weekend. Some things were more expensive for one, some things were more expensive for the other. To answer this question, researchers randomly identified 20 products sold at both stores and determined the selling price. So would this be a dependent or independent? Oh, we already know it's going to be dependent. So we're identifying 20 products and we're comparing the prices. So it's dependent because we have the exact same thing for both and the prices are related in some way. I have a big spreadsheet that did that this weekend and I felt very lame, but you know what? I got cheap things. So that one's dependent. They are related in some way. All right. So for our proportions, we have a crazy looking formula. Back to our z-scores. Personally, the z-scores were always my favorite. They made the most sense to me. Okay. That's the square roots. And we have to note we have P1 hat, P2 hat, and P hat. These are all slightly different. So your P1 and P2 hat are your proportions of group 1 and 2 as appropriate. So those are what we're used to. The just P hat with no subscript This is the proportion, like a combined proportion, let's call it. So we take all of group one, all of group two, put them into one thing and add them all up. We have a formula for this, which is pretty much what I just said. We take all of the group one plus all of the group two all over the total number in group one plus the total number in group two. So I would say your X sub one is the total number in your special group, or if you fit a certain criteria in group one. Do that there for a sec. Got my calculator today, so if you have one, that would be great. I can get my phone calculator out, but it's not quite the same. Make it work though. Okay. So. All right, we'll do an example using this. And we're gonna use our z-scores like we did before. So your alpha, your null hypothesis, your alternative hypothesis is the same. We're not gonna hit that again. We've done that a lot of times. So in this example, we have a clinical trial of Nasonex. 3,774 people with allergies were randomly divided into two groups. Patients in group one got the placebo, or no, sorry, patients in group one got the Nasonex, group two got a placebo. So of the patients in the experimental group, 547 reported headaches. Of the patients in the control group, 368 reported headaches. So can we conclude that Nasonex causes more headaches than the other one? We're using the 0.05 significance. So that is a lot of data. Let's scribble it down. So group one, got the drugs. And we had 2, 1, 0, 3 in group one. And those with headaches were 547. Group two did not get the drugs, sad for them. And in this group, we had 1671. And of those, that should be a 2, not a 1. 368 got headaches. All right, so we have to do a couple prelim calculations before we can plug it in our formula. So the first thing we want to do is find P1 hat. So we take our 547 divided by 2103. And this gave me 0.260. My second one, I get 0.220. All right, and then my just plain p hat I take my 547 plus 368 all over 2103 plus 1671. What things I'm getting? I'm gonna need this number, this number, this number, this number, and this. This is a one-tailed test. So our Z crit is going to be plus or minus 1.645. This would be the number we look up. We've done that a bunch of times too, so. Okay, so that crazy Z formula we are gonna use. So Z0 equals P1 minus P2, the hats. So I get 0.260 minus 0.220, ouch, divided by P hat, which is 0.242. 1 minus that, 0.758. I never leave myself enough space. 1 over my N1 is 2103 plus 1 over 1671. Forty-two times 0.758, 0.183436. All right, I'm gonna divide and then add these up. So 1 divided by 2103 plus 1 divided by 1671. 0.0010739552. The other one, square root of 0.183436. I just divide. All right, 0.04 divided by parentheses 0.2483 times 0.03277. Oh, good. That gives me roughly 2.85. Ideally, if you do this, you leave your big numbers in your calculator and just keep calculating as you go. I forgot my good calculator, so we make it work. But this is actually what I got earlier when I did this, so yay. Put there for a sec. Okay, before we draw our conclusions, we should note that the experimental group, the Nasonex group, has a bigger value than our other groups. So it seems like they have more headaches than the other. So that's the direction we're comparing this. So we'll use a positive z-score. And if we draw our happy little diagram, our z-crit is right here. That was 1.645. Draw my favorite little blue zone. So our value is here-ish, 2.85. We are in the blue, so that means we have a significant difference. So we're going to reject the null hypothesis. So we say there appears to be a difference in proportion of users with headaches I said that poorly today, but that's okay. So we have a significant difference. It seems like the people who use the Nasonex get more headaches than the people who don't. So not a huge amount, but it's interesting to know. All right, we have two pieces remaining. One of them, I'm just going to give you the formula. The second one we're going to work on, just because we've done the formula for this one before or similar. Actually, no, we'll probably do this. All right, so our confidence interval we get P1 hat minus P2 hat plus or minus. You take your Z alpha over 2 times P1 hat 1 minus P1 hat all over N for our total number of users plus P2 hat 1 minus P1 hat all over N. So this will be our interval. We say, hey, we think the actual amount is somewhere between this and this. We're 95% certain of that. So it's a plug and chug sort of formula. So we're 95% certain our real value falls between these, where A or B are the upper and lower bounds for this formula. We've done similar formulas, so I feel okay about that. The last thing from this section is a sample size estimate. So this should be, we've done similar, but we'll look at this one because it's a little different than we've done lately. So if we want a particular confidence within a margin of error, we're going to use this. So to obtain a 1 minus alpha times 100 confidence interval with margin of error E. So we're saying, hey, we want it within 2 percentage points. So that's our margin of error. That would be 2 in that case, or 0.02. We're going to say the total number in our sample needs to be P hat 1 minus P1 hat plus P2 hat 1 minus P2 hat times Z alpha over 2 over our error rate squared. So all I'm doing here is taking the equation we had above and solving it for our N instead of our confidence interval. So say we're given a group we want within 3 percentage points, so 0.03. They say our alpha is 0.05, and they give us the two proportions, 5.11 and 7.52. So we would look up our Z alpha over 2. It's going to be 1.96. We've done that many, many times. Okay, if we want to figure out the number in our sample, we plug it into that formula above and solve. So I get N equals 0.511 and I subtract, I'll get 0.489 plus 0.752 to 1.96 over 0.03 squared. Mm. 0.96 divided by 0.03. I get 65.3 repeating. Square that. Two, 2, 4, 9, 8, 7, 9 plus 0.186496. 436,374 times that monster. 4268 gives me about 1862.6. Okay. We're looking for a number in our population. Assuming we're talking about people, but things work too. We can't have half of a person. So no matter what our decimal is, we have to bump it up to the next whole number. Even if it were something where we would round down normally, we always go up. So we need at least 1863 in our sample. So always go up to the next one. And that's 11.1. I'm going to give you the formula for 11.3 and we'll do some examples next time, but it works a lot like 11.2 did last week. I'll give everybody a sec. I see some people still writing. Well, 11.3, we're comparing means again. Anytime we have a mean, we have a t-test. And we have independent samples this time. So thing one doesn't affect thing two. They're not matched. We're just two samples. So our stat for this. Your S is your standard deviation, your X bar is your mean, your N is the number in that sample. So most of those should be pretty familiar. We've done them so many times. The degrees of freedom for this one is a little weird. For your degrees of freedom, you look at your N1, so number in sample one versus number in sample two. That should be a 1, not a 2. We're going to take the minimum. So if the number in sample one is smaller than sample two, we're going to take sample one minus 1, or vice versa. So you take the smaller of those two numbers, and that's your degrees of freedom. Okay. That is all I have on my sheet about this one today. We're gonna have a confidence interval and such, but we'll get that next time. So yeah, I'm gonna stop my video and then I will start.